Welcome to the deep dive. You hit upload on that video or you
Yeah.
tap play and it just works. Seems almost magical, instantaneous.
It really does.
But today, we're going behind that simple click. We want to unpack the truly staggering scale, the hidden architecture needed to run a global platform, something like YouTube.
Oh, absolutely staggering. The complexity under that smooth interface is, well, it's immense. And the numbers we looked at, the 2020 stats, they really drive it home.
What kind of numbers are we talking?
We're looking at a system supporting, get this, 2 billion monthly active users.
2 billion monthly.
Monthly. That's like, what, a third of the internet?
Yeah.
And they're watching 5 billion videos every single day.
5 billion views a day. That scale it's hard to even picture. And it's not just about eyeballs, is it? It's big business.
Huge business. The sources pointed out $15.1 billion in ad revenue back in 2019, and that was up 36% from the year before. So massive growth, too.
And the sheer network load.
Right. Think about this. YouTube is responsible for something like 37% of all mobile internet traffic globally. Just one platform.
Okay, so our mission for this deep dive then is clear. We need to take that massive scale, that global reach, and figure out how you design the core parts.
Exactly. We're going to focus, really drill down on solving 2 fundamental and frankly brutal problems. First, how do you get lightning-fast video uploads?
And second,
How do you guarantee smooth, buffer-free video streaming for everyone, no matter their device or, their internet connection?
right. So to make this manageable for our design discussion, let's set a target scale. Maybe not 2 billion users, but something still huge.
Yeah, let's aim for designing for, say, 5 million daily active users, DAU. Still a massive number, but gives us something concrete to work with.
Okay, 5 million DAU. And what are the key requirements for this system, the non-negotiables?
Well, the big ones are low cost, and we'll talk a lot about cost. High availability obviously needs to be scalable, reliable, and naturally secure. Encryption is key.
You emphasize low cost there. Seems like that's more than just a nice to have.
Oh, it's absolutely critical. It's maybe the single biggest driver for almost every architectural decision we'll discuss. We can actually demonstrate why with a quick back-of-the-envelope estimate using our 5 million DAU figure.
Okay, let's do it. A reality check right up front. What are the assumptions?
Let's keep it simple. Assume maybe just 10% of those 5 million users upload 1 video per day.
So that's 500,000 uploads daily, and the average video size, HD video is pretty big these days.
Let's be conservative. Say 300 megabytes per video on average. Some are smaller, some much larger, but 300 megabytes is a reasonable starting point.
Okay, 500,000 videos times 300 megabytes.
That works out to 150,000 megabytes, which is 150 terabytes.
150 terabytes of new video data every single day.
Exactly, and that's just the raw ingest. Storing that is expensive, sure, but it's actually the delivery costs that really bite.
The streaming cost,
Yeah.
egress. Right, getting the video out to the viewers.
That's the killer. Let's run another quick calculation. Assume a content delivery network, a CDN, charges maybe 2 cents per gigabyte transferred. That's, a plausible rate if you're buying huge volume from a provider.
Okay, 2 cents a gig. And our 5 million users, how much are they watching? Let's say maybe 5 videos each per day. Seems reasonable?
Sure, 5 videos.
Yeah.
Average size. Depends hugely, but let's ballpark it. If you run those numbers, even with conservative estimates for video size and watch time,
What does it come out to? Ballpark.
you're looking at roughly $150,000
Per day.
is for streaming.
Per day. Just for the CDN bandwidth costs.
Wow. Okay, just let that sink in.
Yeah.
$150,000 daily. Even if you get massive discounts, that kind of number forces your hand, doesn't it?
Absolutely. It tells you immediately that waste is unacceptable. Optimization isn't just a feature. It's like the fundamental requirement to even stay in business at this scale.
That cost pressure really frames everything else we're going to talk about, especially when we get to the optimizations later. Precisely. It dictates so many choices. Which brings us neatly to the foundational architecture. Given that scale, that cost pressure, the very first decision has to be, what do you build yourself versus what do you leverage?
Yeah, do you really try and build everything from the ground up, like your own global storage and delivery network?
The answer from pretty much everyone is a hard no. You absolutely do not build everything from scratch if you can help it. Building a truly scalable blob storage for petabytes, exabytes of video, or your own global CDN, that's incredibly complex, incredibly expensive.
Even the giants often don't do it all themselves, right?
Exactly. Look at Netflix. They famously rely heavily on AWS, Amazon's cloud. Facebook for years used third-party CDNs like Akamai for a lot of their distribution. Building these things is a massive undertaking.
So for our deep dive, the pragmatic approach, the realistic starting point, is definitely leveraging existing, proven cloud infrastructure for the really hard parts anyway.
Right, specifically high-capacity, durable blob storage for the video files and a global CDN for the delivery. That lets us focus on the application logic.
Okay, assuming we use those building blocks, what are the core high-level components we need to design and manage?
We can break it down into roughly three main pieces. First, obviously, you have the client.
That's the user interface layer, the apps, the website.
Yep, mobile apps, web browsers, smart TVs, game consoles, anything the user interacts with to upload or watch video.
Okay, component one, client. What's next?
Component two, the CDN, the content delivery network. We're leveraging it, but it's a distinct component. This is where the final, ready-to-play video files live, geographically distributed.
So users get the video streamed from a server nearby for low latency.
Exactly. It caches the content at the edge, close to the viewer.
And the third piece, the brains of the operation.
That's what we generally call the API servers, or the backend, the application layer. These servers handle basically everything else.
Everything that isn't the raw video stream itself.
Pretty much. Think about it. Users sign up, log in, managing sessions, figuring out video recommendations for your feed, updating metadata like titles and descriptions, handling comments, likes.
And critically for our discussion today,
Critically, they handle the logic for video uploads, like generating those special secure upload URLs we'll talk about later. They orchestrate the whole process.
okay, client, CDN, API servers, got the big picture. Now, we need to zoom in on the actual processes. You mentioned two critical flows.
Yes. The rest of our discussion really needs to follow these two paths. Number one, the video uploading flow, getting content in, and number two, the video streaming flow, getting content out smoothly.
Let's start with getting the video in part two, the video uploading flow. Seems simple to the user, but you said it's complex behind the scenes.
Oh yeah. From a systems perspective, it's a highly parallel operation designed for speed and resilience. The first key thing is that the system immediately splits the user's single action into two parallel processes.
Why split it?
Speed, mostly. It lets the system work on different things at once. Flow A is the big one, uploading the actual massive video file itself, the data path.
And flow B?
Flow B is the metadata path, updating all the information about the video, its title, description, who uploaded it, privacy settings, tags, you name it. This is much smaller, much faster to process.
Okay, let's follow flow A first, the journey of the actual video bytes. Where does that raw file go right after leaving the user's device?
It lands in what we'll call original storage. This is some kind of highly durable, probably cloud-based blob storage. Think of it as input buffer, specifically designed to hold these potentially huge raw files.
It just sits there.
Not for long. As soon as the file upload completes and it's registered in original storage, that triggers the next step. The transcoding servers get notified.
Ah, transcoding. This sounds like the heavy lifting part.
It absolutely is. These servers fetch the raw video file from original storage and start the complex process of converting it.
And what happens after transcoding finishes? You mentioned parallel outputs.
Right. This is clever. When transcoding is done, two things happen more or less simultaneously. First, the newly converted, streamable video files, probably multiple versions, are written to a different storage area. Let's call it transcoded storage.
Okay, separate storage for the processed file.
Yes. And from transcoded storage, they get pushed out, distributed to the CDN edge servers all around the world. That makes them ready for streaming.
That's the first output path. What's the second?
The second path is much simpler. A notification, just a small message saying, transcoding complete for video X, here are the details, gets put into a completion queue, like a message queue.
So a message queue acts as a buffer. Why is that important?
It decouples the system.
Yeah.
The transcoding servers don't have to wait around to confirm that the database got updated or anything. They just fire off that message and can move on to the next video. It improves throughput.
Makes sense. So who picks up that message from the completion queue?
Dedicated workers, let's call them completion handlers, they pull messages from this queue. Their job is basically bookkeeping.
What kind of bookkeeping?
They take the information from the message, like which video formats were created, what are their URLs on the CDN, and they update the main metadata database.
Ah, connecting the video data to its information.
Exactly. And they'll probably update various caches as well to make information retrieval faster. Only after this database update happens can the API servers actually know the video is ready and list it for playback to users.
Got it. That whole flow hinges on that central step, Video transcoding. Let's unpack that. Why is it so essential? You can't just store the original file.
Almost never. There are several crucial reasons why transcoding, or video encoding as it's also called, is absolutely non-negotiable at scale. We can maybe break it down into 4 key reasons.
Okay, reason 1.
Storage reduction. Raw video, especially high definition or 4K footage, is enormous. We're talking hundreds of gigabytes per hour sometimes. Transcoding uses compression algorithms, codecs, to drastically shrink that file size. Remember our 150 TB per day? Compression makes managing that feasible.
Makes sense. Saves a ton on storage costs. Reason 2.
Compatibility. Your users are watching on iPhones, Android phones, laptops running Windows, Macs, Linux, smart TVs. They all support different video formats and codecs. Transcoding converts the uploaded video into standardized formats like HLS or MPEG- that will play reliably everywhere.
So it ensures anyone can watch it, regardless of their device. Okay, reason 3.
Smooth playback, which ties into reason 4, adaptive streaming. This is really key for user experience. Transcoding doesn't just create one output file, it creates multiple versions of the same video at different quality levels and bitrates.
Like a 1080p version, a 720p, a 480p.
Exactly. Maybe a high-quality 1080p for strong connections, a medium 480p for average mobile, and a low 240p for poor signal areas.
And why is that adaptive?
Because the video player on the user's device can then intelligently switch between these versions on the fly based on the current network conditions. If your connection suddenly gets worse, it seamlessly drops to a lower quality stream without buffering.
Ah, so that's how it avoids the dreaded buffering wheel. That's huge for keeping people watching.
It's absolutely critical, especially on mobile networks, which can be unreliable. You mentioned the video structure itself involves containers and codecs. Can you clarify those?
Sure. Think of the container like a .mp4, .mov, or .mkv file as the box or the wrapper. It holds everything together. The video stream itself, one or more audio streams, maybe subtitles, chapter information. It defines how these pieces are organized.
Okay, so the container is the structure. What are the codecs then, like H.264 or VP9?
The codecs are the actual compression and decompression algorithms. They're the highly complex mathematical recipes used to shrink the video and audio data, trying to throw away information that the human eye or ear won't easily notice to make the file smaller. Then they reverse the process during playback.
Got it. Container holds the streams, codecs compress, decompress the streams. Now, for that adaptive streaming to work really smoothly, you mentioned something earlier, GOPs, group of pictures. How do they fit in?
Right, GOPs are fundamental to how digital video is structured, and they're essential for efficient streaming and processing. A GOP is basically the smallest chunk of a video stream that can be decoded independently.
Independently, meaning you don't need data from before it to start playing it.
Exactly. Think of it like chapters in a book. You can open the book to chapter 5 and start reading. You don't need chapter 4. A GOP is typically a few seconds long. It starts with a keyframe, an iframe, which is a full picture, followed by frames that only store the differences from the keyframe or preceding frames, P frames and B frames.
So if the player needs to switch streams, say, from 1080p down to 480p because the network dropped, it doesn't have to wait for the very beginning of the file.
Precisely. It just needs to find the start of the next GOP in the 480p stream. Since GOPs are only a few seconds long, the switch can happen very quickly, almost seamlessly, right at that GOP boundary. Without GOPs, adaptive streaming would be practically impossible.
Okay, that makes sense. GOPs enable fast seeking and stream switching. So given how vital and computationally expensive this whole transcoding process is, we really need to understand the architecture that manages it.
Yeah, let's dive deeper into that. This brings us to part 3, the transcoding architecture and this concept of a directed acyclic graph, or DAG model. Why use something that sounds so, well, academic?
It sounds complex, but it's all about managing flexibility and parallelism efficiently. See, transcoding isn't just one task, it's often a whole sequence of tasks. And crucially, not every video needs the same sequence.
What do you mean?
Well, some creators might want specific watermarks applied. Others might upload videos with multiple audio tracks that need syncing. Some videos might only need basic low-resolution versions, while a professional studio upload might need 10 different high bitrate formats plus HDR processing. A fixed, rigid pipeline would be incredibly wasteful.
Ah, so the DAG is like a customizable workflow for each video.
Exactly. A directed acyclic graph is just a way to represent a set of tasks and their dependencies. Directed means tasks flow in one direction. Acyclic means there are no loops. You can't have a task depend on something that depends back on it. It defines which tasks can run in parallel and which must run sequentially.
So for each video upload, the system generates a specific DAG, a specific processing map.
Correct. Programmers or system admins define all the possible types of tasks the system can do. Then, based on the uploaded video's properties, resolution, format, user settings, the system constructs a DAG for that specific video. For example, the generate thumbnail task and the encode 720p video task might run in parallel.
But maybe an add watermark task has to wait until the encoding is finished.
Precisely. The DAG defines those dependencies. It provides abstraction and enables massive parallelism because unrelated tasks can run concurrently on different machines.
What are some typical tasks you'd find in a video processing DAG?
The sources mention several common ones. There is usually an inspection task first check if the file is valid, not corrupted. Maybe scan for policy violations before you waste compute resources. Then multiple video encoding tasks for all the different resolutions and bitrates needed.
Okay.
You'd also have thumbnail generation, extracting keyframes to use as preview images, watermarking if needed, maybe tasks for processing or syncing different audio tracks. It's highly configurable.
Right. So to actually manage executing these complex dynamic DAGs for potentially millions of videos simultaneously, you need a pretty sophisticated architecture. The sources break this down into about 6 main components.
Yeah, 6 core interacting parts. Let's start with the preprocessor. It's the first stop after the raw video lands in original storage.
With its main job, getting the video ready.
Sort of. It has a couple of critical, sometimes overlooked responsibilities. First, video splitting. This is where the incoming video stream gets divided into those manageable GOPs we talked about. It segments the video based on the keyframe alignment.
Okay, it chops it up. What else?
Crucially, it caches the segmented data. It stores these individual GOP chunks and their associated metadata, like timing info, in some kind of temporary but reliable storage.
Why cache it right away?
Reliability and retries. Imagine a 2-hour video starts transcoding. An hour in, one specific encoding task fails due to a random glitch. If you didn't cache the GOPs, you might have to restart the entire process, maybe even the download from original storage. With the preprocessor's cache, you can just retry the failed task on that specific GOP chunk. It saves a huge amount of time and wasted work.
Smart. So it splits and it caches. What else?
Its other main job is DAG generation. Based on configuration files and maybe analyzing the video properties, the preprocessor actually builds that specific task graph, that DAG, for this particular video.
Okay, so the preprocessor creates the workflow map. Where does that map go next?
It gets handed off to the DAG scheduler. The scheduler's job is to take that graph, which represents dependencies, and break it down into concrete stages or individual tasks that can actually be put into a queue to be executed. It linearizes the parts that need to be linear and identifies the parallel parts.
So it translates the map into a to-do list?
A smart to-do list, yeah. And it puts those tasks into the queue system, ready for the next component, which is really the traffic cop of the whole operation. The resource manager.
The resource manager. Sounds
Yes.
important. Managing resources, like servers.
Exactly. It's all about efficiently allocating the computational resources, the servers or workers, to the tasks that need doing. This is vital for maximizing throughput and keeping costs down. You don't want expensive servers sitting idle.
How does it manage that allocation?
It typically maintains several internal queues. There's the task queue, usually a priority queue, holding all the tasks spat out by the DAG scheduler, waiting to be run. High priority might go to shorter videos or paying customers, for example.
Okay, a queue of waiting jobs.
Then there's the worker queue. This keeps track of all the available task workers, the machines that actually do the encoding, etc. It knows which ones are busy, which are free, maybe what their capabilities are.
And the third queue.
The running queue, which basically tracks which specific task is currently assigned to which specific worker. It's the live snapshot of the system's activity.
So who actually makes the decision? Who matches tasks to workers?
That's the brain within the resource manager, usually called the task scheduler. It constantly looks at the task queue, finds the highest priority task, looks at the worker queue, finds an available suitable worker, and then assigns the task to the worker, moving the pair into the running queue. When the task completes, the worker goes back to being available.
Sounds incredibly dynamic and optimized, like a high-speed matchmaking service for compute jobs.
That's a great analogy. It has to be incredibly efficient to handle the load.
And the entities actually doing the work assigned by the scheduler.
Those are the task workers. These are the compute instances, the servers, that execute the specific jobs defined in the DAG. Could be video encoding, audio processing, thumbnail generation, running analysis, whatever the task requires. There might be different pools of workers optimized for different types of tasks.
Right, and all these components, preprocessor,
Yeah.
scheduler, workers,
Yeah.
they need to share data during the process, right? The intermediate files.
Absolutely. That's the final piece, temporary storage. This isn't the original storage or the final transcoded storage. It's high-performance storage used during the DAG execution. It might be a mix, maybe fast blob storage for the video-audio chunks, the GOPs, and perhaps even faster in-memory caches for small metadata that needs to be accessed frequently by different tasks.
And this temporary data gets cleaned up afterwards.
Yes. Once the entire DAG for a video completes successfully and the final outputs are safely in transcoded storage and pushed to the CDN, all the intermediate data in temporary storage associated with that job can be purged.
Okay, we've built this complex, pretty robust pipeline for getting video in and processed. But we keep coming back to that $150,000 a day number for streaming costs. We absolutely have to optimize.
Now we get to part 4, optimisations. And yes, cost is a huge driver here, but so are speed and safety. Let's tackle optimization 1, speed and parallelism first.
How can we make uploads even faster or feel faster?
A big win is implementing resumable uploads, and this ties directly back to our discussion about GOPs and chunking. This optimization happens mostly on the client side.
So the user's browser or app does something clever.
Yes. Instead of trying to upload the entire video file as one giant monolithic block, the client application can pre-split the video into smaller chunks, ideally aligned with those GOP boundaries we talked about.
So it sends the file piece by piece.
Exactly. Chunk 1, chunk 2, chunk 3. The server acknowledges each chunk. Now imagine you're uploading a 1 GB file on shaky coffee shop Wi-Fi if the connection drops when you're 95% done.
Without chunking, you start all over again. Infuriating.
Right. But with chunking, the client knows chunks 1 through 95 were successfully received. When the connection comes back, it just resumes by sending chunk 96. It makes uploads feel much faster and way more reliable, especially for large files or unstable connections.
It's a huge user experience improvement. What's another speed optimization?
Reducing physical distance, we can use proximity upload centers.
Sounds like building more data centers.
Not necessarily building new ones. It's often about cleverly repurposing existing infrastructure. Remember the CDN, it has edge servers all over the world to deliver content quickly.
Yeah, for streaming out.
We can use those same edge locations as upload points. So if you're a user in, say, Sydney, Australia, instead of your upload request going all the way to a main data center, perhaps in the US, the client is directed to upload the video to the nearest CDN edge node in Sydney.
So the big file travels a much shorter distance initially.
Exactly. It drastically cuts down the latency for the initial upload. The edge node then handles the potentially longer, more optimized transfer back to the central original storage or processing centers. But for the user, the upload feels much quicker to complete.
Clever infrastructure reuse.
Mm.
Okay, third, speed optimization. You mentioned decoupling earlier.
Yes, loose coupling through the use of message queues. We saw this between the transcoding servers and the completion handlers, but you'd use this principle aggressively throughout the system.
So putting queues between different stages, like between downloading the file and starting the preprocessing, or between preprocessing and scheduling.
Absolutely. Every time you hand off work from one distinct component or service to another, putting a queue in between makes the system more resilient and parallel. If the encoding farm, the task workers, gets backed up for a few minutes,
The preprocessor doesn't just stop working.
no, it keeps processing new uploads and just puts the resulting tasks or GOP data notifications into the queue. The downstream system, the resource manager and workers, will catch up when it can. It prevents a slowdown in one part from grinding the entire pipeline to a halt. It's essential for maintaining high throughput.
Makes sense. Speed is covered.
Yeah.
Let's move to optimization 2. Safety and security. We're letting potentially millions of users upload data directly into our cloud storage. That sounds risky. How do we control that?
You need very strict controls. The primary mechanism here is using pre-signed upload URLs.
Pre-signed URLs. How do they work?
When a user's client, the app or browser, wants to upload a video, it first contacts one of our API servers.
Yeah.
It says, hey, I want to upload a video file. The API server does some checks as the user logged in. Are they allowed to upload? If everything checks out, the API server doesn't just give the client the direct address of the original storage bucket. Instead, it generates a special, unique, temporary URL. This URL has cryptographic signatures embedded in it. Think of services like Amazon S3's pre-signed URLs or Azure's shared access signatures.
So it's like a single-use ticket.
Exactly. It's a ticket that grants very specific, time-limited permission, may be valid for only 15 minutes, to upload one specific file, sometimes matching a specific name or size, to a specific temporary location within our original storage. The client then uses that URL to upload the file directly to the blob storage.
And the storage system itself validates the signature.
Yes. The blob storage service verifies the signature and the permissions encoded in the URL. If it's valid and hasn't expired, the upload is allowed. If not, it's rejected. This completely prevents unauthorized clients from accessing or messing with the storage system directly. The API server acts as the gatekeeper.
Very secure. Now, what about protecting the content itself, specifically things like copyright protection for the creators?
That's a multi-layered approach. The sources mention a few key techniques. First, sophisticated digital rights management (DRM) systems.
Like Apple's Fair Play or Google's Widevine.
Exactly. These are complex systems that integrate with the video player. The video content is encrypted, and the player needs to securely obtain a license key from a license server managed by our API tier before it can decrypt and play the content. This prevents unauthorized copying and playback.
Okay, DRM is one layer. What else?
Simple, strong AES encryption on the stored video files themselves. Even if someone somehow managed to access the raw files on the CDN or in storage, they'd just get encrypted gibberish without the correct decryption keys, which are managed securely.
So encryption at rest and managed decryption for playback. Is there anything more visible?
Yes. The third common technique is visual watermarking. During the transcoding process, remember the DA, a task can overlay a visible image onto the video. This might be the platform's logo, the channel's logo, or sometimes even a faint, unique identifier tied to the specific user session viewing the content.
So if someone screen records it and re-uploads it.
That watermark is still there, potentially identifying the source or just acting as a deterrent.
Right. Okay, safety and security covered. Now, back to the big one. The money. Optimization 3, cost reduction. You said this ties into the long tail.
Yes, understanding the long-tail distribution of video popularity is absolutely fundamental to cost optimization at scale. It's a classic pattern you see everywhere online.
Explain the long tail in this context.
It means a very small number of videos, the head of the distribution, are incredibly popular. Think viral hits, major music videos, movie trailers. They get billions of views.
Okay, the superstars.
Then there's the long tail, a massive number of videos that get very, very few views. Maybe it's an old family video or recording of a niche local event, a tutorial on a very obscure topic. These might get watched only a handful of times, maybe even 0 times after the first week.
So most videos are actually not popular at all.
Exactly. The vast majority of the library sits in the long tail. If you treat every video the same store, multiple encoded versions on the expensive CDN globally, you'll go broke, serving content that almost nobody watches.
So how do we apply this long tail insight to save money? Strategy 1.
Strategy 1 is selective serving from CDN. You only put the most popular videos, the head and maybe the upper part of the tail, onto the prime real estate, the global CDN network.
And the rest, the millions of rarely watched videos.
You serve those from cheaper, maybe centralized, high-capacity storage systems that you operate yourself. We called it transcoded storage earlier. Perhaps it's a large storage cluster. Access might be slightly slower than the CDN, maybe a fraction of a second, more latency. But the cost savings on egress fees are enormous because you're not paying CDN rates for every single view of Aunt Mildred's cat video.
Okay, differentiate serving based on popularity. Strategy 2.
Yeah?
Ties into transcoding.
Yes, on-demand encoding or lazy encoding. For those long-tail videos, why bother pre-transcoding and storing, say, 10 different versions, different resolutions, bitrates, if maybe only the 480p version will ever be requested, and only once?
So you wait until someone actually asks for it.
Exactly. For a very unpopular video, you might only store the original uploaded file, or perhaps just one standard web-friendly version, like 720p. If one day someone with a specific device requests a 360p version, then the system triggers a quick, just-in-time transcoding job to create that specific format. Or you simply store the versions that have been requested and don't proactively create ones that haven't.
That must save a huge amount on storage for the transcoded files.
Massive amounts. Storage isn't free, especially when you multiply it by millions of videos and multiple versions per video.
Okay, strategy 3 for cost saving.
Regional content distribution. Apply the same popularity logic, but geographically. If a video is trending wildly in Brazil, but nowhere else.
You don't need to push copies of it to CDN edge servers in Japan or Germany.
Precisely. You analyze viewing patterns and only distribute content widely within the regions where it's actually popular. This again saves on both CDN storage costs, paying for space on edge servers, and inter-region bandwidth costs, transferring the files between data centers or CDN nodes.
Makes sense. Be smart about where you place the data. Is there a final, more extreme cost optimization?
The ultimate step taken by the real giants like Google, YouTube, Netflix, Facebook is to reduce reliance on third-party CDNs altogether. This means either building their own proprietary CDN, which is incredibly complex and expensive,
Cool.
or doing something even smarter, partnering directly with internet service providers, ISPs. They make deals with the big broadband and mobile carriers around the world.
What kind of deals?
They basically co-locate cache servers inside the ISP's network, sometimes right in their local facilities. It's often called ISP caching or establishing a network edge. When a user on that ISP requests a popular video,
It gets served directly from the cache inside the ISP, never even hitting the public internet or a third-party CDN?
exactly. This dramatically reduces the streaming service's bandwidth costs because they're not paying expensive transit fees, and it gives the user an even faster, better experience because the content is physically closer. It's a win-win, but requires massive scale to justify those partnerships.
Right, you need to be sending a significant chunk of their traffic, like that 37% mobile figure, to make it worthwhile for the ISP.
Precisely.
Okay, incredible optimization strategies, but even with all this, things will inevitably break. Part 5. Fault tolerance and error handling. How does a system this complex deal with failures?
It has to be designed for failure from the start. The sources simplify this by categorizing errors into two main types for handling purposes: recoverable errors and non-recoverable.
Oh, it's a recoverable error.
Something transient, temporary. Maybe a network blip causes a chunk upload to fail. Or one specific transcoding task fails because the worker machine had a momentary glitch. The system expects these. The standard playbook is simple. Retry. Try the operation again, maybe a few times, perhaps with a small delay, exponential backoff. Often, the transient issue will resolve itself.
And non-recoverable errors.
These are fundamental problems. The uploaded video file is corrupt or in a completely unsupported format. Or the inspection task flags it for violating policy. UGJ illegal content. Maybe the DAG definition itself is broken.
What's the playbook then?
Stop processing immediately. Don't waste any more resources on it. Log the error clearly. Maybe notify the user if appropriate, example, upload failed, invalid file format, and terminate all downstream tasks associated with that specific video processing job. Retrying won't help.
Okay, let's run through some specific failure scenarios. The error handling playbook. What if an upload chunk fails from the client?
The client retries sending that chunk a few times thanks to the resumable upload mechanism.
What if a specific transcoding task fails on a worker?
The resource manager notes the failure, marks that task instance as failed, and the task scheduler simply requeues the same task for that specific GOP or video segment to be picked up by a different healthy worker. The DAG ensures it only retries the failed step, not the whole process.
What about the core infrastructure? What if an API server goes down?
API servers should be designed to be stateless. This means they don't store critical session information locally. All the state is in the database or caches. So, if one server fails, the load balancer directing traffic simply stops sending requests to it and redirects them to other healthy API servers. Users might not even notice.
Stateless makes scaling and fault tolerance much easier there. What about the stateful parts, like the metadata database? That sounds critical.
Extremely critical. That's where replication comes in. You always run databases in a primary replica or master-slave setup. All writes go to the primary master. Reads can go to the replica slaves.
So if a slave database server dies,
Read traffic is simply directed to the other available slaves, and you spin up a new server to replace the failed one and sync it. Minimal impact.
and if the master database server fails, the one handling writes.
That's more serious, but manageable. An automated system, or sometimes manual intervention, performs a failover. One of the up-to-date replicas is promoted to become the new master. There might be a very brief window where writes are paused, but the service recovers quickly.
And if a task worker machine dies mid-task.
Similar to a task failure, the resource manager detects the worker is unresponsive, marks any task it was running as failed, and the task scheduler will reschedule that task onto a new, healthy worker.
Okay, sounds like redundancy and retries are key themes. How does this impact scaling the different parts?
It varies. Scaling the API tier is relatively easy because, as we said, it's stateless, need more capacity, just add more identical API servers behind the load balancer. That's horizontal scaling.
But the database,
Scaling the database tier is much harder because it's stateful. Simple replication helps with read load, but eventually a single master database can't handle the write load or the dataset becomes too large for one machine. That's when you need sharding.
remind us what sharding is again.
Sharding means partitioning the data horizontally. Instead of one massive database holding all video metadata, you split it into, say, 100 smaller databases, shards. Maybe shard 1 holds data for videos whose IDs end in 00, shard 2 for IDs ending in 01, and so on. Or you could shard by user ID.
So each shard only manages a subset of the data.
Exactly. An application layer or a proxy needs to know which shard holds the data for a specific video or user, but it allows the database tier to scale writes and storage almost indefinitely by adding more shards. It adds complexity, though.
Definitely sounds more complex than just adding more web servers.
Yeah.
Now, briefly, how does all this compare to live streaming? We've focused on video on demand, VOD. Are the challenges different?
Very different in some key ways, though many components are similar. The biggest difference is latency sensitivity. VOD can tolerate some delay in processing. Live streaming needs near real-time delivery, usually sub 10 seconds, sometimes even lower.
Does that mean different streaming protocols?
Often, yes. While HLS and DAH, common for VOD, have low latency variants now, live streaming often historically used protocols like RTMP for the ingest, pushing from the broadcaster's encoder to the server, and might use WebRTC or other specialized protocols for ultra-low latency delivery. The emphasis shifts from batch processing efficiency to continuous low latency flow.
And the parallelism we designed for transcoding. Less critical for live.
Sort of. For live, the video is already coming in chunks in real time from the broadcaster. So the transcoding still happens chunk by chunk, but you don't have the same opportunity for massive parallel processing across an entire finished file like in VOD. The focus is on processing each incoming chunk as fast as possible to keep the end-to-end delay low.
Error handling must be different too, right? No time for many retries.
Exactly. If a chunk fails to transcode in a live stream, you can't just retry for 30 seconds. The stream has moved on. You need faster error handling, maybe quickly trying to switch to a redundant stream, or inserting a slate image, or just accepting a moment of glitchiness. The tolerance for recovery time is much lower.
Okay. One final requirement mentioned in the sources, video takedowns. The system needs a way to remove content.
Absolutely essential for legal and policy reasons. Whether it's due to a copyright claim, like content ID match, or a violation of community guidelines, illegal content, hate speech, etc., the platform must be able to remove videos quickly and effectively.
How does that work technically?
It usually starts by updating the video's status in the metadata database, marking it as removed or unavailable. This immediately prevents the API servers from serving it in search results or recommendations. But critically, you also need to purge it from the CDN.
Tell the CDN to stay serving it.
Yes. You need an API call to the CDN provider to invalidate or purge the cached copies of that video URL across all their edge servers globally. This ensures that even if someone has a direct link, it stops working quickly worldwide. It has to be a fast, automated process triggered by the policy or legal decision.
Right. Wow. Okay, stepping back from the weeds, this deep dive really shows how that simple upload or play button hides an incredible amount of complexity.
It really does. We went from just clicking a button to designing parallel processing flows, sophisticated transcoding pipelines using DAGs, complex resource management, multi-layered caching, and storage.
All underpinned by constant optimization driven by that massive scale and especially the eye-watering cost of data transfer.
And the architecture itself, using queues for decoupling, leveraging cloud services, designing for failure, understanding the long-tail distribution, that structure is what makes handling the scale and flexibility even possible.
The core insight really seems to be managing that tension between providing instant access to everything and the astronomical cost associated with the rarely accessed long tail of content.
Absolutely. Which leads us to maybe a final provocative thought for you, the listener, to chew on.
Go for it.
We designed this system largely around the economics of the long tail, optimizing heavily for content that might not be watched often. So how might you design a streaming service differently if it was built only for short-form, high-velocity content? Think TikTok style, where videos explode in popularity for maybe 48 hours and then effectively disappear. Would that drastically simplify the architecture? Could you perhaps ditch on-demand encoding or change the CDN strategy if you knew content had such a short, sharp life cycle?
Interesting. How would you optimize if there was no long tail to worry about? Something to definitely ponder.
Indeed.
Well, that's all the time we have for this deep dive. Thanks for joining us.
Thank you.